Let's look at this quiz problem. This is question number 2 and quiz number 3. Estimate the Henry law constant or Henry law partition coefficient Kh and Kh prime. Remember, Kh prime is dimensionless, and Kh is the one without dimension, with dimensions. He wanted at 25 Celsius and 5 Celsius of the following compound using the data provided. Well, the data is not provided, but you have to go to the textbook and find the first one. 1,2-dichlorobenzene. He wants you also to draw the structure. 1,2-dichlorobenzene. So it's a benzene ring. Double bond, and double bond. 1, 2. So 1, 2. 1, 2. Of course, there's 2 chlor, so dichlor, and it's a benzene ring. So this is the structure of the first one, 1,2-dichlorobenzene. The data is not provided, but you have to go to the textbook and find out the data for what is the melting point, melting temperature. If you go to the book, it is minus 17 Celsius. What is the boiling point of 1,2-dichlorobenzene? The boiling temperature is 180. 180 Celsius. What is the vapor pressure for 1,2-dichlorobenzene? 0.0019 atmospheric. And what is the solubility of 1,2-dichlorobenzene? It's 6.3. This is from the appendix. You could look at it and Teams. I gave it to you. You could Google it, and you could look for the solubility of 1,2-dichlorobenzene, vapor pressure, boiling point temperature, and melting point temperature. Okay. So we could notice here the melting point and the boiling point. So we could assume that here it's going from air to water because this is obviously water, liquid. So if you want to find out the Henry partition coefficient from the notes, it's Kh is equal Kh sat, vapor pressure on atmospheric liquid over the solubility on atmospheric liquid. So, this is equal to that. So now, what is the vapor pressure at 25 Celsius? This is at 25 Celsius. This is equal 0.0019 atmospheric over the solubility of that compound. Atmospheric over molarity, that's 3 atmospheric over mole per liter. Now, he also wants Kh dash which is the dimensionless. It's by dividing Kh sat over RT. Kh sat is 3 atmospheric per molarity over, well, here I am going to give you R, 0.082 per mole Kelvin, and the temperature is, let's see, what is the temperature here? 25. So 25 plus 273, that's 298. So that's 298 Kelvin. So Kelvin with Kelvin, atmospheric with atmospheric. and molarity with molarity, and you end up with unitless. So this is 0.12. So we found KH and we found KH brine or dimensionless for 1,2-dichloropenzene. That's not it. Since we have everything at 25 at room temperature, he also want cold conditions at 5 Celsius. Okay, let me just go down. Okay, so we need to find out at 5 Celsius. We can estimate the change in KH by using the equation that we did in the notes and in the Excel sheet. By using this equation and assuming that delta H Henry is constant. Okay, so ln KH minus delta H, it's called as Henry over R 1 over T plus the intercept. If we assume that KH is equal KH sat, then delta H Henry may be approximated by the differences between delta H VAP and delta H solubility. Okay, and that is the equation we have in the notes. So ln, just try to put this estimation, minus delta H minus delta H solubility, okay, over R 1 over T plus the intercept, a constant. Okay, let's go ahead and calculate the KH at 5 Celsius, and we're going to insert all the reference temperatures and the temperature of the interest into the previous equation and obtain the differences. So ln, just look at the Excel sheet, you'll see the equation over there. This is similarly the same equation that we're going to be using right now, equal. What is ln KH at 298 at 25 Celsius plus, remember we were adding delta H VAP, that's the slope, minus delta H solubility over R, and that is the slope, times 1 over the T for 98, T temperature of the 98, okay, minus the new temperature, which is 5 Celsius, but we have to change this to Kelvin. So what are we going to plug here? Let me just change this to black. Well, we're going to plug here that KH, we have it here, and we're going to use KH at 25. So here it's going to be ln 3 plus, okay. From the book, you could find that delta H VAP value can be found around 45.8 for 1,2-dichlorobenzene. So this is 45.8 kilojoule per mole. The delta H solubility can be obtained from the extrapolation of values in the table that you have in the Excel sheet and also in the book, table 5.4. We can assume that this, we can assume it not 1,2-dichlorobenzene, but we can assume it dichlorobenzene, which is about the intermediate in size between naphthalene and fluorine. So delta H solubility should be about the half. Let's see, delta H solubility should be 0.5 the delta H solubility of fluorine, which is 15.5. That is from table 5.4. Plus delta H solubility of naphthalene, somewhere in the middle. Okay, so this is plus 9.9 for naphthalene. And this would give you 12.7 kilojoule per mole. So this is 12.7. And R for this R, we use 8.314 because the unit are not the same as the one. Since we have kilojoule now, we should use the other R. And this temperature is 5. 5 is 2. Let's see, 273 plus 5. It's 87. It's 278. So then 3. This is kilojoule. So kilojoule. Okay. Over. So this is equal to 0.14. Okay, so this is ln KH. This is ln KH. So KH would be equal to E to the power 0.14, and that will give you. Let me just use my calculator and check it. If 0.14. This is 1.15, and that is atmospheric. Molarity. And if you want to find out KH prime, just by dividing, but not with this R, the other R, this R, 0.082 atmospheric liter per mole Kelvin, because we have a lot of R with different units. This would give you KH 1.15 atmospheric per molarity over 0.082 0.08 atmospheric liter times the temperature. That's 5, so 5 is 278 Kelvin. Kelvin with Kelvin, atmospheric and molarity with molarity, you will end up with 0.05. And that is unitless. So we're gonna check everything, but we have to be careful because the next one, I'll go for the next one because the next one seems to be the solid. So, what happened here? Okay, so let's look at the second one, which is atrazine. Well, you have to find the melting point. I'll give you the melting point because to see if it's solid or liquid. So it's 174. You can see that that's the melting point, and look at the boiling point. 395. It's beyond 100. So which means that at 25 Celsius, it is solid for sure. Look at the solubility. (1.6 10 to the minus 4 molarity). I will let you draw the structure on your own. But now, since we are dealing with solids and we cannot find the vapor pressure, and because solubility, we are giving it in solids, we only need to estimate the vapor pressure of the solid, because Henry law for atrazine is equal the pressure of the solids over the solubility sat for the solids. To do that, we first need to estimate the vapor pressure of the subcooled liquid using the equation we have in the notes, and I will try to give you this equation here. Ln pressure of the subcooled liquid is equal minus Kf 4.4 plus ln the boiling temperature 1.8 boiling temperature over temperature minus 1 minus 0.8 ln temperature boiling temperature over the regular temperature. Okay. This is a very weird compound, atrazine. The Kf should be assumed 1.1. So this is Kf. And Kf should be assumed 1.1 for atrazine to account for the polar effect of the pyridine. And of course, if you draw it, you can see the amine fractions of that compound. So this is 1.1, 4.4. And the boiling point, we know it, 174, but we have to convert it to Kelvin. So you should add 273 to it. So 174 plus 273, that is 7, 14, really, 447? Oh no, oh no. This is the melting point. We should account for